All right, we're going to go ahead and jump into this today. We're going to be talking about elements, compounds, and mixtures. So the first thing I want to say is we need to be able to designate between these. We want to be able to compare and contrast them. So looking at what these differences are, the first thing I want to say is that an element is going to contain just one type of atom. And so if we look at that, we can see that, let's say, for example, we have a helium atom. So that's going to have two protons. I'm going to go ahead and color those red. It's going to have two neutrons. And then on the outside, you're going to have two tiny little electrons that are floating there on the outside. I'm going to draw those very small because remember, electrons are very small. And so if you look at the periodic table, what you're going to see is you're going to see helium. You're going to see its atomic number is 2, and then you're going to see a mass number down below. And just because you can see here, there's four subatomic particles in the nucleus. Its number is going to be somewhere near 4. The atomic mass is going to be 4, but I just want you to know for future that that can kind of change because you can actually have more or less neutrons or electrons, but we'll get there later. Just understand that most of the time, the number down below is going to be about twice the number on top, and this number on top, that atomic number, is always going to be equaling the number of protons. But this atom, you're only going to have one type of atom. And you can see right here, this little, if you look in this example, this model, there's one type of circle that's there. Next, a compound is going to have two or more different atoms that are joined together. And if you look at the compound over here, you can see the large blue circle and the two small, tiny orange circles. And so an example of this would be H2O. And what that means is you have two atoms of hydrogen and you have one atom of oxygen that are joined together. And you can see here, there's two of these, one of these. Total is 3. And if you look at the example of that molecule there, you're going to see that that is actually 3 atoms that are joined together to make the compound. But the idea here is as 2 or more different atoms joined together. And another way to say that is 2 or more elements that are combined. Okay? Now, a blend contains 2 or more different substances that are only joined together, physically joined together, not chemically. And that would be a mixture. So everything that exists, whether it's a solid, liquid, or a gas, is going to be an element, a compound, or a mixture. And a mixture, if you look at this mixture, you'll notice that here you have 2 atoms of the same type. That does not qualify as a compound. So here I have some compounds, like this one's a compound right here. That's an element right there. And then this, even though you have two atoms, they're not different atoms, they're the same atom. That's going to be an element as well. So a mixture can contain both elements and compounds. It can contain both of those things. Okay? All right. So when we talk about solutions, I want you to know that a solution is a type of mixture. And in this, we have two things. We have a solvent and a solute. So if you think about this, if you were to make, like, let's say a pie graph here, right? The solvent is going to be the larger portion of whatever it is you're mixing in the solution. Solute is going to be the smaller portion of whatever it is that you're mixing. So you can see here, this is small. Now, the one thing I'm going to say about the solution when it's made is it's going to be what we call homogeneous. And what that means is that it is the same throughout. If you were to look at it and you look at how the little particles are distributed, they are the same throughout. What it is not a suspension. So a suspension would be something like this, where you have all the particles at the bottom, but that is not what it is. And that, in contrast, this one right here would be heterogeneous because it's not the same throughout. So what makes a solution is that it is a homogeneous mixture, meaning that it is the same throughout. It is all the same. If you take your eye and you look at this portion, that is going to be the same as if you take your eye and look at this portion. It's going to be exactly alike. Now, when we talk about pure substances are going to have one type of particle. One type of particle. And that particle could be an atom or it could be a molecule. So a molecule, by definition, is going to be two or more atoms chemically joined together. And I know you don't know what that means yet, but that's okay. Okay, so they are two more atoms joined chemically. So here you can see that this right here for letter number 1, that's going to be molecules, because even though they're one type of atom, they're joined together. Okay, over here, these are going to be atoms, and then you have a mixture of atoms and molecules down here. So which one of these is pure? So pure means one type of particle. So the ones that are pure here, I'm going to go ahead and put a blue check on the ones that are pure. It's going to be number 2 because you have one type of molecule here. Number 3 because you have one type of atom. Number 4, this is Roman numeral 4. That is not, because you have the white ones and the red ones. Number 5 is going to be a yes, because you have these that are what we call diatomic molecules. Anytime you have two atoms that are the same type that are joined together chemically, that would be called a molecule, but they are not compounds. Some examples of these would be hydrogen gas, oxygen gas, nitrogen gas, and you can see that little 2 there means you have 2 of those. So these are diatomic molecules because it's the same one that's joined to itself. Helium gas, chlorine gas. You get the point. Like, it's just like the elemental symbol with like a little 2 there, a subscript 2. So we have diatomic molecules right there. Compounds. So when we have compounds, how do compounds and elements compare and contrast, create a Venn diagram? So I'm not going to do all of this for you, but I want you to know how to do this. If you go back to the previous statements that I made, you'll see a lot of information that's very pertinent to you. But both of these are going to be pure substances. And if you're going to write elements on one side and compounds on the other side. And again, I'm not going to do all of this for you, but the big thing here is that an element is going to have one type of atom, and a compound is going to have 2 or more elements. Okay? Now, again, where it gets confusing is the word molecule, because I just told you that you could have 2 atoms that join together to each other that are the same type, as in oxygen gas. That's technically a molecule, but it's not a compound. But all pieces of compounds are molecules. That's confusing, I get it. But just go ahead and try to complete this on your own. And if you have questions, let me know. But I want you to also try to give me examples, right? So some examples would be oxygen. Over here would be water. Okay, so give me at least 3 examples of both of these as you're completing that. And then we'll go over it together if you have questions. This is a great graphic organizer. We have homogeneous and we have heterogeneous. So homogeneous is going to be the same throughout. And then with heterogeneous, you can see different layers. You can see different layers or different components, particles. I'm going to write components here. Okay, so we have suspensions and we have colloids. Now, those are the 2 types of heterogeneous. With homogeneous, we have two types. We have solutions and we have alloys. Now, what an alloy is where you take two different metals and you mix them together. So an example that would be copper and tin, and I believe that makes brass. I could be mistaken on that one, but brass is not an element, but copper and tin are elements, so we can mix those together and make an alloy of brass. Alloys are just mixtures of metals, and when you melt them together, they mix really well. But remember, a solution is going to have the solute and the solvent. And remember that solvent is a larger portion. So if you had some salt and water, that salt is going to be the solute, whereas the solvent is going to be that water. It's the larger portion of it. Okay, so it gets evenly dispersed. It's even throughout. That's what makes it homogeneous. So homogeneous means it's the same throughout, whereas heterogeneous means that you're going to be able to see differences. There are differences in there that you're going to be able to spot. Now, the one thing I want to say is about these suspensions. Like, so if you take oil and water and put them together, what you're going to basically see there is you're going to see a layer of water, and then on top of that, most of the time, you're going to see a layer of oil just kind of floating. If you put food coloring in that water, it's going to make it look really neat when you gaze into it, because it's going to have like a nice little visual effect. Colloids are kind of their own thing. They are bizarre. And what makes them strange is that they will, their particles are like, basically they should be a suspension, but the particles in a colloid are too tiny to settle. So they are technically heterogeneous if you look very closely, but with the human eye, they're going to look like a solution, but they're really not. So the particles are basically, they can be distinguished if you grab a microscope, but the one thing about these is they're going to produce this effect with light called the Tyndall effect. But here's some examples. We have milk, we have jello, we have fog. So these are not, like I said, these are not technically solutions, but they do look like that when you first take a glance. But upon further inspection, you'll see that they're more like a suspension. It's just the particles are too tiny for them to drop down because of gravity. All right, another example here. Look at that. You can see that in this solution, you have even disbursement. Even disbursement. And that's why we call these homogeneous. So again, homogeneous means that it is the same. If you look down here and if you look up here, you're going to see, it's not settling. It's all mixed in together, mixed in evenly in the different places, top and bottom and middle. Here's some examples of alloys. Oh, look, well, no, brass is copper and zinc. Oh, I had copper right. But look at bronze. Bronze is copper and tin. Solder is going to be tin and lead, and then stainless steel is kind of complicated. You have iron, chromium, and nickel. What makes stainless steel superior to iron? First of all, it will not rust. If you think back to your chemical changes, it will not rust, and is able to bend. Okay, but again, all these alloys, they're also going to be homogeneous. They're also going to be homogeneous. All right, just like solutions. So remember, it's a homogeneous mixture. So, you could think of an alloy as a solid solution. That would be a great way of describing that to someone if they hadn't known. But the cool thing is metals can mix really easily, so they can be evenly mixed together. You're not going to see like chunks of lead and then chunks of tin. It's all going to blend together, and those little atoms are going to kind of allow themselves to move around, and it's going to be a beautiful homogeneous mixture. Here's an example of a suspension. Now this is actually a type of salad dressing that your parents might use, or maybe you'll have one day when you go to a fancy restaurant. But down here you have some vinegar, and then over here you have some oil. Okay, and if you shake this up, if you shake it, you will disperse it. Okay, you'll disperse it, you'll make it move around, and you'll see it looks like this. It appears to be homogeneous, but if you wait, let's say about 2 minutes, what you're going to see is you're going to see it become heterogeneous again. So again, a suspension is heterogeneous, and that means it looks different throughout. There's no homogeneity. That's a big word for you. It looks different. And a way to kind of remember, what the word means is if you look at it, it's kind of suspended in the air above the other portion. The oil and the vinegar really do not mix well, but that's why you have to be really precise when you define these different mixtures. Again, this one looks homogeneous, but if you give it a moment, what you'll observe it settling. Now, if you mix salt and water together, the salt is not going to settle. It's going to be mixed in there. You can leave it out for 2 days and it's not going to settle. It's going to stay where it's at. And so that's the big difference here. With the balsamic vinegar and the oil, it will settle out, it will separate. Now, when we look over here, what we're seeing is this is actually called the Tyndall effect. So this is called the Tyndall effect. And this is a great way to tell whether or not something is a colloid. Okay, if we go back and we look at the different kinds of mixtures, we have two major categories. We have the homogeneous and we have the heterogeneous, which is like the ones that are different. And of those two, we have suspensions and we have colloids. All right, and with our homogeneous, we had solutions and we had the alloys. We don't do a lot with alloys, but solutions are easy to make. You can make them in school, not a problem. But when we get over here to colloids, remember, colloids are going to be weird. They kind of look like a solution, but they really are not. So look at this flashlight. The flashlight is going through the solution, and as it does, there is no effect whatsoever. It just goes right through. The light goes right through it. The light can pass through it. When it hits the colloid, and see, here's a mixture of water and milk. When it hits the colloid, it will spread out. And so that spreading out of light is called the Tyndall effect. Tyndall effect, if you wanted to define it, it is the spreading of light due to tiny particles. The spreading of light due to tiny particles. So the particles are kind of separating, and again, you can't see them. They're very, very small. So the particles inside, milk and jello and fog, those little water droplets are very tiny, so they can't really get out of the way. They're not really mixed in between the other molecules. They're kind of like hanging out, obstructing things. And so that's why you have this Tyndall effect. The person who discovered it, his last name was Tyndall, and that's how we got the name. But you're going to see this with, that's why if you're driving in foggy weather, you don't want to turn your brights on because it'll blind you. You can kind of see here's some more examples of that Tyndall effect in colloids. You have the light passing through the trees on a foggy day. You have that nice scene. And again, you have that scattering of light. And that's only going to happen with colloids. And once again, to remind you, colloids are going to be a heterogeneous mixture because they do not settle out completely. Go ahead and take a moment to look over your study guide questions, make sure that you complete those, and then if you have questions, let me know, and then I will assist you with whatever you have questions regarding. Thank you very much.